Hi and welcome to another episode from Spiral Physics Education. So we're going to be looking at characteristics of waves, and so it's going to be a lot of looking at very specific terms and what they mean for waves. So these are going to include how waves are absorbed, how they are transmitted, how they're reflected as well, with two different types of reflection. We're going to be looking at specular and diffuse reflection, also about refraction, a little bit of introduction into what that means, and also an introduction to diffraction as well. And all of those terms, waves behave differently depending on their wavelengths. So they're not all the same. So we're going to be looking at what happens to wavelengths with those different types of characteristics for waves. So what's really helpful for you to know in this lesson will be what a wave is, to know about frequency and wavelength, also about wavefronts, because we're using those quite a bit in this episode, and wave speed. And if you're not sure about any of those terms, then do check out some of the other videos on the channel to help you get up to speed on those. So let's have a look at transmitting and transmission of light to start with. And this is all to do with the ability of a wave to pass through an object. So if an object passes straight through an object completely, it's completely transmitted. Its transmission is 100%. It hasn't been absorbed or reflected or anything else. It's passed straight through, and that's what transmission means. So transmission is the act of transmitting. And to give you an example of that is that when we look at water on a bright sunny day, water does transmit visible light, but not all of it. Some of it is reflected at its surface. So what we can say there, the transmission of light is reduced because the water reflects some of it. So I'll give you an example of the use of the word there in an appropriate sentence. So in terms of absorbing and transmitting are related to each other, because if you have an object that absorbs all of a wave, then what it will do, it will absorb all of its energy. And what that means is that it won't be able to transmit. If you think about it, that makes sense. If transmission is a wave passing through an object, if it absorbs the wave completely, it's not going to transmit. So transmission of the wave does not take place if it is completely absorbed by an object. So the next thing is reflection of a wave. And reflection is really the scientific term, a fancy way of saying bounces. So wherever you feel the urge to say it's bouncing off, don't. Use the scientific words. Use in this case reflecting. Students often use bouncing when what they should be saying is colliding as well. But in this case, reflection is the scientific name for light bouncing off a substance. So I'm going to show you a little bit about that. So I'm going to use something called a ray box to produce a ray of light. So here's our ray box, and we're going to look at a ray of light reflecting off a mirror. And what we usually draw is a ray of light being a fine beam there, and that fine beam is going to reflect off that surface. And if we look at the wavefronts, that's what would happen to the wavefronts. So the wavelengths are the same before and after the reflection, and we draw those wavefronts so that they're perpendicular to the direction in which the energy is transferred, or the direction in which the wave is moving. So what we can also do is draw a ray diagram for this. So whenever we draw ray diagrams, we must add something called a normal, and that's the normal there, that dashed line. And that normal is at right angles to the surface that the wave is interacting with. So in this case, the wave is interacting with the mirror. So we draw at the point where the wave touches the mirror a normal at right angles to that surface. So that's our normal, and our normal is always a reference point. So other things that we can label on this is the ray of light that's coming out of the ray box that is incident on the mirror. Well, we call that the incident ray. And the ray of light that reflects off the mirror, well, we call that the reflected ray. And what we also do is that from that normal we measure an angle. So that angle there from the normal to the incident ray is called the angle of incidence. And similarly, the angle that is from the normal to the reflected ray is called the angle of reflection. And I'm sure you've done this in the laboratory. If you were to do lots of different, measured lots of different angles of incidence and lots of different angles of reflection, you would come up with the law of reflection, which states that the angle of incidence is equal to the angle of reflection, and that's the law of reflection. However, there are two different types of reflection. So we're going to look at specular reflection to start off with. And when you look at specular reflection, what happens is the angles in which the reflected rays bounce off, the angles are all the same. Just like this. And that means that you're going to get a nice shiny surface. So rays of light that reflect off a mirror, that's an example of specular reflection, because all the rays of light that bounce off with the same angle. Diffuse reflection is slightly different though, because the rays of light that reflect off the surface all scatter or reflect off in different angles, and what you get there is a duller reflection, and is very, very different to specular reflection, but that gives you the idea about why surfaces that are dirty and uneven look dull. So let's have a look at refracting. So this is just an introduction to refraction. So refraction is really a scientific name for bending. And rays of light bend or refract because their speed changes when they move from one substance into a different substance. So I'm going to give you a bit of an example of that by using a ray box again. And we're going to look at a ray of light that passes into some water. So it's going from air on top to water underneath. And what we're going to do, we're going to follow what happens to this ray of light. But we're going to look at the wave fronts just to see what happens in a little bit more detail to that wave when it goes from air into water. So here are the wave fronts that are moving through the air part. And when that ray enters the water, it's going to refract, it's going to bend like this. And now we can look at what's going to happen to the wave fronts and that, or how they're affected by that. So this is quite a good animation to show you about the speed and also about the wavelengths. So notice that the wave fronts in the water are moving slower. The wave has slowed down in the water, and that's because the water is denser. It's more optically dense, and that means the wave is travelling slower in the water compared to air. Notice also that the wavefronts are closer together in the water, and that means that the wavelength of the light has decreased because it's slowed down. So the act of slowing down the wave has bent the wave, it's refracted the wave, and also it's caused the wavelength to decrease as well. So if we draw a normal to the point in which that ray of light is entering the water, what we can also say is that the ray of light has refracted or bent towards the normal. And that's caused by slowing down. And that means also that the wavelength has reduced during that refraction. So let's have a look at a little bit of an introduction to diffraction. So diffraction is the spreading out of a wave when it interacts with either a gap or an aperture, or indeed an object. So we're going to look at some examples of waves diffracting or spreading out. And again, diffraction is a scientific term for spreading out. So what we've got here is a wave, and we're looking at the wave fronts here. And those wave fronts are going to progress towards the aperture, and then this is how we draw diffraction. It's the spreading out. Notice that the wavelength before and after diffraction is unchanged. Diffraction does not change the wavelength of the wave. So what we can do now is make the wavelength longer. And that's going to affect what happens to the amount of diffraction. So here now we've got the same aperture, but what we have is a much larger wavelength than before. And that's going to cause greater diffraction. So waves that have a greater wavelength diffract more. They spread out more. And waves with shorter wavelength diffract less. And what we're going to look at is what happens when we make the aperture, the gap, smaller. So here we're going to make the aperture smaller, and we're going to have a wave that's got around about the wavelength that's about the same size as the aperture. And when the wavelength and the aperture are approximately the same size, we get this optimal diffraction, this semicircular diffraction pattern occurring. And that's another characteristic of diffraction. Maximum diffraction occurs when the wavelength and the gap are around about the same size. So diffraction also occurs around objects, not just through gaps. So here we've got an object, and what we're going to do is we're going to move a wave towards it, and when it gets in contact with that object, it diffracts into the space beyond it, although there is a slight shadow area. In this example, it shows that the wave diffracts into that area beyond the object. And again, if you had a longer wavelength being used here, the diffraction would be greater. And if you had a wave with a much shorter wavelength, then there'd be less diffraction occurring, there'd be less spreading out. So I hope you found this introduction to characteristics of waves useful. Don't forget to subscribe to the channel to check up on other videos that I'm going to post, and hopefully they'll improve your understanding of physics and boost those grades for you. And we'll see you next time on Spiral Education Physics. Goodbye.